So in chapter 7, guys, we did hypothesis test with one sample only. We get one sample and then we study, just this sample, and we try to make conclusion about the population. In chapter 8, we're going to be comparing two samples. So we're going to be doing, hypothesis tests with two samples to compare two populations. For example, if someone makes a claim that men earn more money than women, you would need to collect the data from the men's salaries. You could need to collect data on the women's salaries and compare the two. So, and this is actually where most the common, hypothesis testing problems. For example, when they did the study, on the effectiveness, of COVID-19, it's not one group that they brought, they brought in two groups, guys. One group got the treatment, got the vaccine, and another group did not get anything, and they compare the results of the two groups. So one group, they call it control group, and the control group doesn't get any treatment, no changes in it. And the other group is called the treatment group. This is the ones that, for example, if you are talking about the vaccine, that's the one who got the vaccine. And then they monitor, just the two groups, and then they compare them. And that's why it involves, just two samples. You get one sample from one population, another sample from another population, and then you compare results. So what we're going to learn in section 8.1, how to determine whether two samples are independent or dependent. And we're going to introduce the two sample hypothesis test for the difference between two population means or two population proportion. Remember, in chapter 7, we studied hypothesis testing for the mean and for the proportion. We're going to do the same thing, but it's going to be, instead of one mean, two means, and instead of one proportion, it's going to be two proportions. If you guys, since we studied in chapter 7, this and that, mean and proportion, since in chapter 8, we're comparing two of them, how would you label those here? If you wanted two of those, how would you label them? Like that? They look the same. How do you distinguish the two?
Like 1 and 2.
Exactly. We're going to compare in, that's it. That's the only difference, guys. And here P1 and P2. And remember, here he would give you X bar, he would give you N, and he would give you, for example, sigma. Look over here, he's going to give you X bar 1, he's going to give you N1, he's going to give you sigma 1, X bar 2, N2, sigma 2. And when he replaces sigma by S, this is going to be called S1 and then S2. For a proportion, guys, remember there are two pieces of data that are given, X and N, in chapter 7. What is going to be in chapter 8? X1 and N1. And can someone tell me what is it going to be for the second population or the second sample?
X2 and N2.
Exactly. That's the difference, guys. So rather than working with one group, you'll be working with two groups and comparing two groups. But the same steps, step 1, 2, 3, 4, 5 are exactly very much the same. And that's what makes chapter 8 interesting, because this is usually the case, just of hypothesis testing. So independent samples. We say two samples are independent if one sample selected from one population is not related to the other sample selected from the second population. These are not related. Look, this is an example here. They have nothing in common, not related. Now, dependent samples, they call them paired or matched samples. Each member of one sample corresponds to a member to the other sample. And I gave you, just a visual. Look, this member here relates to that member there. This member relates to that member there, and so on. So this is an example visual of a dependent samples, and this is a visual of independent samples. Let me just give you some examples of that. Classify the pair of samples are independent or dependent. Weights of 65 college students before their freshman year begins, weights of the same 65 college students after their freshman year. What do you guys think?
Dependent.
Uh, Of course, they are dependent because it's the same group. It's the same 65 college students. You take their weight before their freshman year, and then you take their weight after the freshman year. So if you put them in two sets like that, they're going to be, just connected with each other. The same students here, that's his weight before the year begins, and that's his weight after the years begins. So they are connected. When they are connected, guys, they are dependent samples. Okay, let's see the second one. Scores of 38 adult males on a psychological screening test for attention deficit hyperactivity disorder. Scores of 50 adult females in psychological screening test for attention deficit hyperactivity disorder. What guys, what do you think?
Independence.
Independence, and guys, it's obvious. Look, 38 males, 38, 50 females, they have nothing to do with each other. It's not the same group. Look, here is the hint for you. If it is the same group listed in the two samples, then they are dependent. If it is a different groups, then they are independent. These are independent. Of course, these are independent. All right. So this is just to tell you the difference between dependent and independent sets. Now, how do we state when we compare two groups? So guys, this is what we're gonna do in this chapter. Let me just get you ready to show you how to state the null and the alternative. We have one population. We're gonna call it a population one. We have a second population, population two. We're gonna compare the means of the two populations. So this is called the population mean one, and this is called population mean two. And we're going to compare the means, which one, like there somebody could make a claim that the mean in the first population is bigger than the mean in the second one, or could make a claim that the mean in the first population less than the population mean in the second one, and so on and so forth. So how do we state the null and the alternative when we compare two sets, guys? It's going to be easier actually than chapter 7, because you will have three scenarios. You always have to pick up one of the three scenarios, guys. There's one scenario. I'm going to have you help me fill this out. And there's a third one. Any guesses, guys? What would I put there? What signs can I put there?
Like for the first one, we could use the equal sign and n equal.
That's one scenario.
Yeah, and then the larger or equal.
Yeah, that's a second scenario.
Yeah, and then the smaller or equal and larger for the HA.
Exactly. That's it, guys. You have to say, you just select one of the three for your hypothesis. There are no numbers here. Like in chapter 7, I said, test the claim that the mean is less than 15. Mean wait time is less than 15 minutes. You just do less than 15 here. No numbers here. It's a mu1 on one side and mu2 on the other side. So he either, if he asks you, test the claim that the two means are equal, that would be your hypothesis right here. If he asks you, test the claim that the first mean is larger than the second mean, that would be your hypothesis here. If he asks you, test the claim that the first mean is less than the second mean, that would be your hypothesis. And that's it. You just list them and move on to step number 2. So let's take you back here. And these are the statements, guys, that you have to choose from. You just select one of those statements. And you guys, you always remember the defendant is not guilty. We assume the defendant is not guilty until proven otherwise. And we always assume that the null hypothesis is true until proving otherwise. We're going to begin with the two sample Z test. We call it in chapter 7, guys, Z test. Now we're going to call it two sample Z test when sigma 1 and sigma 2 are known. In chapter 7, it was when sigma is known. Now sigma 1, population standard deviation 1, and population standard deviation 2 are known. Sigma 1 and sigma 2 are known. we use what we call a two-sample z-test for the difference between two population means. Sigma 1 and sigma 2 are known. That's section 8.1. Remember, section 7.2 started with sigma, population standard deviation is known. Here are the conditions, guys, in order to be able to perform the two-sample z-test. The population standard deviations are known. Sigma 1, sigma 2 are known. He has to give them to you. The samples are randomly selected. The samples are independent. And the populations are normally distributed, or the sample size is at least 30. If the population is not bell-shaped, guys, the sample size must be 30 or more. These are the 4 conditions that we have to satisfy. And you're gonna see in the problem, he will list those 4 conditions to make sure that you can perform a two-sample z-test. So how do you perform the test? Watch, guys. Verify that sigma 1 and sigma 2 are known. Verify that the samples are random. Verify that they are independent, and verify that the population are normally distributed and or the sample size is at least 30. If he tell you the population are bell-shaped, you don't need the sample size to be big. If he doesn't mention this, he has to give you a sample size of 30 or more. Okay, and I'm ready now to show you how to do one exercise, guys. Let's begin. That's the first example. A credit card watch group claims that there is a difference in the mean credit card debts of households in California and Illinois. Can you guys tell me what would be the null and the alternative hypothesis? So California, it's going to be the first mean, and Illinois, it's going to be the second mean. And they claim that there is a difference. So which one of the hypotheses, guys, we're going to consider for our problem? First, or second, or third?
The first one.
Will be the first one, correct. And the difference will be this, because that says mu1 is different from mu2. The mu1 will be the mean credit card debt from California, and the mu2 will be the mean credit card debt from Illinois. That's what it's going to be. Okay. The results of a random survey of 250 households from each state. So N1, guys, is 250 and N2 is 250. Are shown at the left or at the bottom. The two samples are independent, guys. So he says they are independent, and he says random. So we already met, guys, the conditions, sigma 1 and sigma 2, let's say if they are unknown. Assume that sigma 1 is 1045 and sigma 2 is 1350. So that's the fourth condition is met. And he says the populations are normally distributed, or each sample size is at least 30. Look, he gave me a sample size of 250, guys. So the 4 conditions of the test are met. We can perform the test. Do the results support the group's claim? Use alpha equals 5%. Yes.
So which one is sigma 1 and which one is sigma 2? Because I see both of them are sigma 1. So.
Oh, that's my mistake. That should have been sigma 2 here.
Oh, okay.
Yep. So assume that sigma 1 is 1045 for California, and sigma 2. He started with California, he labeled it as 1, and then Illinois, he labeled that as 2. And then that's your sigma 1 right here, guys, which is 1045. And sigma 2 is 1350. So are the conditions of the test met? Yes, we just verified all of them, all 4 conditions, they are met. And now we're ready to perform the hypothesis test. Have your calculator ready, guys. So I'm just gonna go to the next page and show you how to do the 5 steps. Step number 1, state the null and the alternative. We decided, guys, that this was gonna be the null and the alternative, and that's the claim. because they said there are difference in the mini credit card debit, guys. Difference. Just read that carefully. It says the difference. If it says they are equal, it would have been the null hypothesis, but it says the difference. Okay. And guys, we're gonna see when the population standard deviation are given, we just use. See the difference between chapter 7 and 8? I just added 2 samples to it. It is the z-test, but it's about 2 samples. And let me show you the test. It's going to be solely based on the p-value. Okay, ready? So you go to stat, tests, and it's number 3, guys. So for section 8.1, it's number 3. Okay, he wants sigma 1. Sigma 1 is 1045. He wants sigma 2, 1350. X1 bar, you see now there are 2 of them. It was 4777. N1 250. You see, he didn't say that the populations are bell-shaped, normally distributed. That's okay. He gave us a sample size which is large enough, so we're good here. X2 bar is 4866. I'm looking at the previous page, guys. N2 is 250 as well. And can a student tell me what is the alternative sign before I move on? First, second, or third?
First.
First, yes, that is correct. And if you guys like to see the p-value in action, it's going to be on both sides. Ooh, huge p-value. Okay. The test statistic Z is negative 0.82. Step number 2. P-value, let me just write this down, guys, and then we're done with the calculator. 4098. What's the decision? Alpha here, he says 0.05. Do you guys agree with me that this number is bigger than alpha? And if it is a bigger than alpha, the decision will be what? To fail, to reject HO. And guys, I'm not going to confuse you here. I'm going to use the exact same technique that I use in chapter 7. I told you in chapter 7, if we fail to reject HO, we start with there is not enough evidence. At the alpha level, 0.05, level of significance. 2. What did I say? Which word do you use? Support or reject? The claim is in HA.
Support.
Support. When the claim in HA, you pick the word support, guys, to support the credit card watchdog group claim. So that means their claim might be not correct. We could not support it. That's it. Not enough evidence at the 0.05 level of significance to support the credit card watchdog group claim that there is a difference in the mini credit card debts of households in California and Illinois. All right. That's the first question. I'm going to do another question and move on to another section. You're going to see, guys, it's redundant. Same stuff. We're going to be doing the same stuff. Let's do this together. And I hope, is this a good indication, guys, enough to tell you that this is a z-test? Look, he says sigma 1 and sigma 2. You know right away it's a z-test once he gives you sigma. A travel agency claims that the average daily cost of meals and lodging for vacationing in Texas is less than the average daily cost in Virginia. So can you guys tell me which hypotheses we're gonna, remember Texas, he labeled that as number 1 and Virginia is number 2. He says the daily cost of vacationing in Texas is less than that of Virginia. So which one is it gonna be? 1, 2, or 3?
Three.
Does everyone agree with the student statement? It is 3. Yes, correct, because this is Texas and this is Virginia, and we want to be Texas less than Virginia, and that is correct. Less than. So I can write him right away, guys. Now you tell me, how do you know that Texas is labeled as number 1? Look, he labeled it right here. He says 1 and Virginia is 2.
Is it always going to be labeled which one is one?
You know what? Usually it is labeled, whatever he begins with, he labels that as 1. Yeah.
Oh,
Most of the, I cannot tell you 100% of the time, but most of the time, yes.
I mean, if it's not labeled like this in
You
a
label it.
table,
You
then the
label
first
it.
one would be 1.
Yeah, usually that's a good practice. Label the first one if you want 1, that's fine.
Okay.
The table below shows the results of a random survey. So the survey is random of vacationers in each state. The 2 samples are independent. So the conditions of the test are met, guys. Assume that sigma 1 and sigma 2 are 2019 and 24 for Texas and Virginia, and that the population are normally distributed. If he says the population normally distributed, then that's the 4th condition is met. At alpha equal 1%, is there enough evidence to support the claim? And you guys, I didn't make up those exercises. It's adapted from American Automobile Association. All right, so it's a 2 sample Z test. I'm ready to perform the test. I strongly suggest later, guys, today, just go back and redo those problems just to make sure that you enter the information properly. And no data here. Sigma 1, you see, they're important, 19. Sigma 2, 24. X1 bar, 234. N1 is 25. X2 bar is 240. 20. Doesn't like look, it is cheaper to go there. They look very much the same. And for the alternative, guys, you can see I put less than mu2. And if you like to draw to see the p-value in action, wow, it's big. So Z is negative 0.91 and p-value is 0.1808. And you guys agree with me, it's bigger than alpha. So decision is failed to reject HO, and the same conclusion as number 1. There is not enough evidence at the 0.01 level of significance to support the claim. To support the travel agency claim. That the average daily cost of meals and lodging for vacationing in Texas is less than that of Virginia. So we could not support their claim. That means probably it's not true what they're saying. They're saying it costs less, just to go to Texas. Well, we could not approve of that. So probably it might cost more or the same. And conclusion, guys, perform a 2 sample Z test for the difference between 2 means in mu1 and in mu2 with independent samples, and sigma 1 and sigma 2 are known. And that concludes section 8.1. Any questions about section 8.1? You guys, you can see the segue now to the second section. Instead of sigma 2 and sigma 1 are known, they're unknown, and he will give us S1 and S2 instead. And what would the test that we will be using, guys? Can you guess what the name of the test is going to be? It's not going to be the two sample Z test. It will be two sample what?
T-test.
T-test, exactly. So just to show you the similarity between what you learned in chapter 7 and chapter 8. And now, this is section 8.2, guys. Testing the difference between means independent samples, sigma 1 and sigma 2 are unknown. S1, S2 are given instead. All right. So a two-sample t-test is used to test the difference between two population means when sigma 1, sigma 2 are unknown, samples are random, samples are independent, population are normally distributed, or at least the sample size is at least 30. So same conditions. The only thing is here sigma 1, sigma 2 are unknown, whereas in the previous one, they're known. Okay. Two sample t-tests for the difference between two means sample independent samples. Verify that sigma 1 and sigma 2 are unknown. The samples are random, they are independent, and that the population are normally distributed. Or if not normally distributed, make sure that you have a sample size of 30 on each. Same steps, guys, the same 5 steps. Okay, HO, same, you either have this choice, that's one choice. If I were in the classroom, I usually have students write them down and I'll just walk around and I'll check them. But it's exactly the same as in the previous section. Or guys, you can tell what the last one is going to be. Actually, some of my students find it easier, just to grasp chapter 8 and 7 because they don't have to worry about numbers on the other side. It's just pick, just one of the 3 selections that you already know of. All right. When it comes to using the calculator, guys, there's something that extra that we have to select, which I'm going to talk about it as I do the problem. So let's begin with the question exercise. The results of a state mathematics test for random samples of students taught by 2 different teachers at the same school are shown below. There shouldn't be a $sign here. Can you conclude that there is a difference in the mean math test scores for the students of the 2 teachers? Okay, can you guys tell me which hypothesis is it going to be, the first set, the second, or the third? He says, can you conclude that there is a difference in the mean math test scores for the students between the 2 teachers?
First one.
Does everyone agree that it is the first one? Yeah, difference means not equal to. I agree. And that's the claim. There you go. All right. We agree, guys. You see here, he gives you S1 and S2. Once he gives you S instead of sigma, guys, you know that this is a 2-sample t-test. Don't try to run. If you try to run the 2-sample z-test, it's going to prompt you for sigma 1 and sigma 2, and you don't have it, guys. So how are you going to do that? You can't. So it has to be the 2-sample t-test. But pay attention. There's something extra with this test that we have to do. See, it's number 4, right after number 3. Enter. Ready? Let's just pay attention to this, please. Stat. Okay, X1 bar. We're good. We have it, 473. I mean, they look close, but I don't know if there is a difference. S1 is 39.7. N1 is 8. You see, the sample size is small, but he says the population are normally distributed, so that's good. X2 bar is 459. S2 is 24.5. And N2 is 18. All right. And the mu1 is not equal to mu2. Okay. Now there's the word pooled. You have to select yes or no. It does make a big difference in the answer. Let me tell you how do you decide whether it is a yes or no. If he says assume that the population variances are not equal, you select a no. And if he says assume that the population variances are equal, you select a yes. So if I go back here, select pooled yes if the population variances are equal, and select pooled no if the population variances are not equal. And since he says here they are not equal, so that means when it comes to pooled, it's going to be a no. The p-value will change, guys, if you don't pick the correct one. You get two different p-values. So it's going to be a no for us here. And I can do a draw. Oh, small p-value. No, I was wrong. So we're going to fail to reject HO again. It's HO day today. We're not rejecting HO. So T is 0.92. 4. There's 3 decimal places for T. 922, sorry. And 3792 for the p-value. Just watch it, guys. 0.3792. And definitely, guys, that's bigger than alpha. I don't care even what alpha is. It is bigger than alpha. You fail to reject HO. Sometimes I throw in the numbers just there, but I didn't expect it's going to be all fail to reject HO here. So the conclusion, there is not enough evidence at the 0.10 level of significance to, and don't let that confuse you guys. The claim is in HA, just use the word support to support the claim that there is a difference in the mean math test scores for the students of the two teachers, that there is a difference. So we cannot support the claim that there is a difference. So probably they do the same. You get the same results in both teachers in the mean math test scores. I'm just copying and pasting the claim for the students of the two teachers. Any questions, guys, about this? So that is the two sample t-test, and again should be obvious to you when you are given S1 and S2, not sigma 1 and sigma 2. You should use the two sample t-test and look for a language for pooled. If he says let's assume population variances are equal, we use pooled yes. If he says population variances are not equal, pooled no when you use technology. We're going to do one more question. And let me show you guys second one. Okay, let's read this together. A manufacturer claims that the call-in range in feet of its 2.4 gigahertz cordless phone is greater than that of its leading competitor. Look here, he didn't label them as 1 and 2, but you can start with the manufacturer as being number 1 and the competitor as being number 2. So if you want, I put manufacturer, and then I put competitor here. And then we need x1 bar, we need n1, x2 bar, n2, and we need s1, and we need s2. All right, you perform a study using 14 randomly selected phones from manufacturer and 16 randomly selected similar phones from its competitor. So you guys agree with me, 14 goes here and 16 goes there. That's the first one. The results from the manufacturer have a sample mean of 230 feet. That's 230. And with a standard deviation of 26, S1 is 26. He didn't say population standard deviation, guys, so it must be S. The results from the competitor have a sample mean of 216 feet with a standard deviation of 32 feet. At alpha equals 0.05. Can you support the manufacturer claim? Assume that the population are normally distributed and population variances are equal. When he says this, guys, remember, when it comes to pooled, it's going to be a yes now. Okay. Who can tell me, first of all, which one is going to be the set of hypotheses? We're testing the claim that the manufacturer range is higher than that of its competitor. So what is it going to be? Number 1, number 2, or number 3, guys?
Number 2.
Number 2, I agree. Remember, guys, number 1, this is the manufacturer, and number 2 is the competitor. Okay, 2 sample t-test. All right, let's perform the test. Stat tests. X1 bar, 230. S1, 26. N1 is 14. X2 bar is 216. S2 is 32. N2 is 16. And we need the alternative hypothesis, guys, which is greater than. Make sure to select it properly. And pooled is yes, because he says population variances are equal. Assume. It's an assumption. That's an equal. And yes. And then if you want to do a draw, you're going to see the p-value on the right now. It's faster if you don't do that, but okay. Unfortunately, p-value is bigger than alpha again. So t is 1.303. P-value is 0.1017. Bigger than alpha, which is 0.05. Failed to reject. HO. I told you it's the day of HO today. So there is not. Fail, there is not. Reject HO, you start with there is. There is not enough evidence at the 0.05 level of significance to support the manufacturer claim. That their range is higher than that of their competitor. And that, guys, conclude the two sample t-test for the difference between two means in mu1 and mu2 with independent samples. Sigma 1 and sigma 2 are unknown. We will do later some more exercises. I have some more exercises in the back, but just to give you a feel, this is how you perform a two sample t-test when sigma 1 and sigma 2 are not known. So what we learned so far, a two sample z-test when sigma 1, sigma 2 are known, and two sample t-test when sigma 1 and sigma 2 are not known. What I'm gonna do now, I'm just gonna skip section 8.3 for now, go to section 8.4. And if you ask me why I skipped 8.3, because it's a little bit heavier than the other sections. So let me just finish 8.4 and then you can spend enough time on 8.3. So that's section 8.4 now. How to perform a two sample z-test for the difference between two population proportions, P1 and P2. That's section 8.4. Okay, three conditions are required to conduct the test. So this is similar to the proportion test, guys, but now since we're doing it with two sets. In the proportion test you learned in chapter 7, you need X and N. Now you need X1, N1, and X2, N2. Three conditions are required to conduct the test. The samples must be randomly selected. The samples must be independent. And the samples must be large enough to use a normal sampling distribution. That is, remember guys, we checked that n times p greater than 5, n times q greater than 5. Now it's gonna be for each sample. N1 p1 greater than 5, N1 q1 greater than 5, N2 p2 greater than 5, and N2 q2 is greater than 5. So we will, I'll demo that in a second and show you. If he asks you to check the conditions of the test, if he doesn't ask you to check the conditions of the test, you just perform the test. So can you guys help me state the null and the alternative here for the proportion? It's not going to be any different from the means, guys. Whatever you did for the means, it's going to be exactly the same. Just change the labels. So you guys agree with me, one could be equal, not equal. One greater than or equal, less than, and this is less than or equal or greater than. That's it. That's his choice number one. I'll call him 1, 2, and 3, and then I'll ask you to tell me which one. No other choices. Cannot come up with a fourth choice here. So to perform a proportion test for two samples, verify that the following conditions are met. State HO and HA, calculate the standardized test statistic Z, calculate the p-value, make a decision to reject or fail to reject the HO, interpret your decision into context. And I think, guys, I'm ready to show you one question here, show you how that works. In a study of 150 randomly selected occupants in passenger cars and 200 randomly selected occupants in pickup trucks. So you guys, you can see that the two sets are, one is for passenger cars. He didn't label them, so we're gonna label them as we read them. And this is a pickup trucks. Okay. Can you guys label 150? What's 150 for us?
N.
Yes, it is N1. Because you have two of those, correct? So that's N1, and then N2, guys, will be 200 randomly selected occupants and pickup trucks. 86% of the occupants in passenger cars and 74% of occupants in pickup trucks wear seat belts. At alpha equals 0.10, I'm going to ask you to label those for me in a second. At alpha equals 0.10, can you reject the claim that the proportion of occupants who wear seat belts is the same for passenger cars and pickup trucks? So which one we're going to use, guys? He says, can you reject the claim that the proportion of drivers who wear seatbelt is the same for passenger cars and pickup trucks? So would it be 1, 2, or 3, guys?
1.
1, I agree. And you guys agree with me that the claim is in HO. Well, actually, he's asking you if you can reject the claim. Once he asks you a question of rejection, be assured, guys, that the claim must be in HO. All right. Who can tell me what did he give us here? That's not X, guys. X has to be a whole number.
Yeah, that's a percentage of X from N. So
that's a P1 hat. And that's a P2 hat. And how do you find X, guys? Do you still remember what I say? X is the percentage of the total. So that will be what? 0.86 times 150. And X2, guys, will be 0.74 times 200. You could do them on the calculator, but if you want to do them separately, you can do that. So if he gives you 2 percentages, guys, he didn't give you X1 and X1, 2. You just take this percentage and multiply by the total. I mean, if I tell you guys I have 80 students and 30% of them are going to get an A, for example, if you want to figure out how many will get an A, just take 30% and multiply by 80. And it's exactly the same thing here. So let me just do that. So 0.86 times 150. If it doesn't turn out to be a whole number, you have to make it a whole number, rounded. So it's 128.9. That's good. And if I take 200, guys, and multiply it by 0.74, it would be 148. Okay. Let me tell you what to do if he asks you to check the conditions of the test. He didn't ask, but if he says verify the conditions of the test, which are here, I'm going to show you how to check them. They're very easy to check. So let's just put them right here. You take N1 150 and multiply it by 0.86, which is the N1 P1 here. And the answer is 129, bigger than 5. Then you take 150 and multiply by the Q hat, Q1 hat. If 80.86, guys, is the, sorry, right here. If the 0.86 is the P1, you multiply by 150, you get 129 bigger than 5. What would be the Q1 here?
1 minus. So.
Yeah, 1. So that will be 0.14. Because 0.14, guys, plus 0.86 will give you 100%. And that is, I think, guys, you agree with me, that's 11. 150, so that will be 21, bigger than 5. Okay, now let's go to the second set. 200 times 0.74. We already did it. It's 148, bigger than 5. 200, 0.7. This is probability of success. Probability of failure, 1 minus. You're correct. So that would be 26. And that's 52, bigger than 5. So all the conditions of the test, guys, are met. You can perform the test. You will only do that if he asks you to verify the conditions of the test. If he doesn't ask you to verify the conditions of the test, you just perform the test. So when we test the difference between two proportions, there is only one test, guys. It's called two-sample prop Z test. That's the only test available here. I'm going to show it to you. Or 2-prop z-test. Let me show you the test right here. You go to stat, tests. You can see it's number 6. 2-prop z-test. 2 refers to 2 samples, guys. 1 refers to 1 sample. We use 1-prop z-test in chapter 7. Now, since we're comparing 2 sets, we use 2-prop z-tests. Okay, and look, he's asking me for x1, which is 129. He's asking me for n1, which is 150. He's asking me for x2, which is 148. N2, which is 200. And now let's see what's the alternative hypothesis, guys. You can see P1 is not equal to P2. I'll select it. And then I'm going to hit calculate this time. So that's a screenshot of what we're doing. Z is 2.73. Again, guys, just do those questions, go back and redo those questions later. Make sure that you match with my answers. 0062, that's a P. Oh, first time, p-value is less than alpha. We're gonna reject HO. There's alpha, 10%. Reject HO. Why? Because the p-value is less than alpha. So we don't start with there is not, there is enough evidence at the 0.10 level of significance to, who can tell me to what? The claim is in HO, guys.
To reject.
To reject the claim. There you go, just copy it. That the proportion of occupants who wear seat belts is the same for passenger cars and pickup trucks. So it's not the same proportion, not the same proportion of people wear seat belt, whether if they wear, in pickup. You guys, I think it's obvious to you that people who drive, just bigger cars and stronger cars tend not to wear, just a seat belt as much as often as people who drive smaller cars, because they know they think that they are more protected, and which is probably, yeah, it is the case. Driving a compact cars is not as safe as driving probably a Ford, 150 truck. So that's why we ended up rejecting the claim that the proportion of people who wear seat belts, the drivers who wear seat belts, is they're not the same. So eventually they are different. There is enough evidence at the 10% level of significance to reject the claim that the proportion of occupants who wear seat belts is the same for passenger cars and pickup trucks. Okay, we're going to do one more exercise and take a break after this. On the proportion, guys. Just 1 second. Medical research team conducted a study to test the effect of cholesterol-reducing medication. At the end of the study, the researcher found that of the 4,700 randomly selected subjects who took the medication, 301 died of heart disease. Of the 4,300 randomly selected subjects who took a placebo means sugar pill, 357 died of heart disease. At alpha equals 1%. Can you conclude that the death rate means a proportion, guys, due to heart disease is lower for those who took the medication than for those who took the placebo. If I label guys N1 and 2, what do I put? What's the title here and what's the title there? Can someone help me here? We have medication and we have what? No medication. So it doesn't label them for you all the time. You just have to label them sometimes. Okay, 4,700 who took the medication. So N1, guys, is 4,700. 301 died of heart disease. That's the number of successes. X1 is 301. Of the 4,300, that's N2. How many died of heart disease? 357. He says, at alpha equals 0.01, you see in medical field, alpha goes low. That's 1%. Can you conclude that the death rate to heart disease is lower for those who took the medication than the one who took placebo? So the medication is going to be P1, guys, and placebo is P2. And which one is going to be, guys? First, second, or third? You want the proportion of death is lower for those who took the medication than those who took placebo.
Second.
Second, I agree, because that's lower, guys, less than. Exactly. I agree. Lower means less. All right, two proportion Z test, as simple as that. All right, let's see. Let's run the test together, guys. Second, sorry, stat tests. It's number 6. Okay, X1 is 301. N1 is 4,700. You see, it's a large sample size. X2 is 357. N2 is 4,300. And we need to check that P1 is less than P2. You can do either calculate or draw. Oh, it's very small p-value. Okay, Z is negative 3.46. And p-value is, all right. You see 3e minus 4, it means you have to move the decimal place 4 digits to the left. Now the decimal place is already here, guys. So you move it 4 digits to the left, it's going to be 0.003. That is the p-value, which is of course less than alpha. Once you see the E there, guys, you know your p-value is almost 0. It's less than alpha. So reject HO. And then there is enough evidence at the 0.01 level of significance to what? A claim is in HA, guys.
To support the
To
claim.
support the claim. Yes, we can support the claim. Remember, when the claim is in HA and you reject HO, if HO is false, HA is true, guys. Remember that. So when you reject HO, you're speaking in favor of HA. there is enough evidence at the 0.01 level of significance to support the claim that the death rate, I'm just gonna copy and paste, guys. I'm just copying this. Due to heart disease, is lower for those who took the medication than those who took nothing, took placebo. So, and in conclusion, guys, you perform a two-sample proportion z-test for the difference between two population proportion P1 and P2. And you need the following information. You need X1 and 1, and you need X2 and 2. Sometimes he doesn't give you X1 and X2, guys. He gives you P1 and P2. You just multiply P1 by N1 to get X1 and multiply P2 by N2 to get X2. So I gave you two different examples, one where you are given X1, X2, and the other one you are given P1 hat and P2 hat. Okay, I'm gonna stop